looking at hypothesis testing of a single proportion. And first stage is that you would set up an alternate hypothesis. A null hypothesis might look like this, that the population proportion is 35%, and the alternative could be that it got bigger. And there's a sample attached to these stories, and maybe you got 75 out of 145, and there should be a significance level attached to that. So the generic story has a null hypothesis. This is what it used to be. It also has we think there's evidence to prove something else is going on. In my particular story, this is bigger than 35. There will be some information to do with the sample, 75 out of 145. Sometimes they don't give you it in this form. This is the form that's actually useful for using SALT, because SALT wants to know the top, bottom numbers. But sometimes they just tell you that the sample was 145 and that p hat was, let me figure what that out would be. Would be, you know, something like that. Now, if you get told the information in this format, like the sample, 52% of them were married and there were 145 people in the sample. If you got the information written that way, you need to find that top number. I mean, we know the bottom number, it's 145, but you need to find this 75. How would you find the 75 in this situation? If I told you this was 52% and there was 145 people in the sample, how would I figure out the top number?
Multiply the two?
Yeah, you just basically multiply the two. You find 52% of 145, or you multiply 0.4552. So you put that whole package together, right? And you will be given, damn it, I've forgotten the name, but essentially it becomes this Z-score. I remember its name now. They called it the test statistic. Can you remember yesterday they went and asked this thing called the test statistic, and I was thinking, I think that's a Z-score, and it ended up being that. But what you're really, really interested in is this guy called the p-value, because this is the key to the whole process. And the argument is, if that p-value is very small, then we have evidence to prove that the alternate hypothesis is true. So if the p-value is tiny, then this will be true. Now, what does tiny look like? Well, we have a test. And the test is the p-value less than the significance level? Okay, since I've got all these numbers set up, let's do a little pretend question using this, right? So I guess I'll have a story. 35% of married couples can't remember when they were married. You think it's got worse? So we asked 145 married couples when they were married, and 52% of them, well, worse, I guess, it's got better, it's got bigger, right? Were asked, and they got it right. 52% of them got it right. So 75 out of 145 got it correct. So we are going to see whether that is evidence to prove that people are getting better at remembering when they were married. So I'm now going to zoom over to here, and we're going to use that SALT button. Fingers crossed. Go. Yes. Is that thing big enough, or do I need to make these screens larger for you? I don't know what kind of TV you're using, or Mona. Is that good enough to see? Okay, so what we're going to do is we're going to make sure that it's set up in one proportion. The number of successes were 75 people remembered when they were married, and it was out of a sample size of 145. And the null hypothesis was it used to be 35. And we want to find out if it's got bigger, right? And then when I hit generate results, we should see up here all the good stuff that we need. The null hypothesis is it's 35. The alternate is got bigger. Do you see that matches what I did have physically written down? There's your test statistic. And do you see how small that p-value is? What's it got? 1, 2, 3, 4 zeros and a 1, 2. So 0.123 zeros. Let's say the question was to 5 decimal places. Okay, we've got everything we need. I'll now go in here and show you what that would kind of look like on paper. Right. We got the p-value. Would you agree that is tiny? Very, very small. So is this fella less than this guy? And when the answer is yes, then we have enough evidence to reject. I don't know if they call it H naught or they call it the null hypothesis. It's the same thing. I'll call it H naught. There really is more to this sentence, but from the ones I've seen in the homework, they only give you that bit. There is a second part to this, and I feel it's worth it putting in. And that's something like, and so we can conclude that the alternate is true. In other words, we can say we have proved that it has got better. Are we cool on that process? Right. So what I'm now going to do is jump back to the homework questions. And we're going to do a real homework question. Looks like it's question 9. Yes. I think I could. Can I check that? No, I can't. Let me do something here, just as a thought that might work. Oh, it's student view. Okay, we're good. 7, 8. Here we go. It's question.
We can't see it yet, sir.
Okay, sorry. Yeah, I'll show you it now. Thanks, Chris. For my eyesight, maybe not for yours, but for my eyesight, I need a bit more. I need to see more. Okay. So, in this story, a standard hypothesis test, a poll was released in the year 2000, found that 48% of randomly selected adults said that they were very happy when given the choice between being very happy, fairly happy, or not too happy. So, okay, it's a pretty simple question to ask. Suppose a journalist who is pessimistic took advantage of this poll to write the headline, "Poll finds that significantly fewer than half American adults say they are very happy." Now, the English language tends to have nuances on it. When someone says significantly fewer, doesn't that make you think it's a lot fewer? But when we say something is significant in statistics, don't we just mean that it's evidence to prove it's true, it's significant? But couldn't that significance be quite minor? Like it's just 1 shy of 50% or a couple of percent. So the usage of that word significant in statistics, that is a correct statement, probably. We're going to find out if it is in a minute or two. But can you see psychologically, it projects a different feeling to the truth. I mean, 48% is less than 50, but significantly less? No, I would say a little less. Right? I might even say it's almost 50%, which is probably even closer to the truth. So we are going to set up all the various stages from top to bottom. And the first part of the story is, if P is the proportion of all US adults who were very happy in the year 2000, go through what they call the 5 steps, and we'll do that, to determine whether this headline is true, justified. And yay, they finally got to tell us the significance level, because sometimes they seem to not mention it. I think last time, didn't they say a standard significance? And we said, okay, it must be 5%, because then they told us anything else. I think we'll have to work on that if they do that again, but it's so much nicer when they just tell you. Now, the null hypothesis here is that it is equal to half the people. And the alternate hypothesis is that it is less than that. Are we comfortable with the null and the alternate based on this story? Right. How do I know it's 50%? Didn't he say it's less than half? Which is another way of saying less than 50%, less than 0.5. So if you know what this guy is, this fella is the same number, but just with equals. So far, so good. Any questions about why I chose 0.5 and less than 0.5?
Why less than?
Say again, Sydney?
Why'd you choose less than for the alternative?
Because he went and said here, significantly fewer than half US adults.
Oh, okay.
So that was the key to that sentence. I'm just, half is just another way of saying 0.5, isn't it? And if you can figure out what's trying to be proved, that ends up being the alternate hypothesis every time. So if you're trying to show that the poll finds less than half, then you're looking for P less than half, which means that the null is always going to be P equals that guy. If you wanted to prove it was less than 20%, then P would equal 0.2 here, right? For instance. Now, this is the various conditions that they talk about. The two that they're really interested in this homework is that it's randomly selected, which we'll assume makes sense. Now, they talk about this thing called NP0 and N1 minus P0. Don't these two things have to be bigger than 10? Remember the 10 rule? Sample's got to be big enough. Now, who is this funny P0 and who is the N? The N is the sample size. And where is it? There we go. The sample size was 1900. So here you would be doing 1900 times P0. P0 is the name we give to this guy. Just a label for it. Right? Do you see the 0.5? So this fella, which happens to be equal to what's that? 950. And this guy is sample size times 1 takeaway P0. Well, if P0 is P5, isn't 1 takeaway also 0.5? But can you imagine one of them was 0.3, the other would be 0.7. If one of them was 0.2, the other one would be 0.8. And this also ends up being 950. So this is the check that the sample sizes are big enough. It's the 10 rule. Is NP0 and N1 minus P0 at least 10? both quantities are at least 10. So we have found the necessary data that all the conditions are met. Are we comfortable with how we went through this bit? So if the next time there's 200 people in the sample and that's 0.4, you will go 200 times 0.4 and 200 times 0.6. And hopefully these two answers will be at least 10. Now, this fella is going to be the z-score, and this guy is going to be the p-value, but to get them, we need to do salt. Now, have you noticed that the p-hat is really this guy here? It's 48%. That's the sample. And I'm writing down, although you can't see it, 0.48. And I'm also writing down n is 1900. That's not the numbers I need for salt. Don't I do that little multiplication so I know how many people said yes out of it? So I got this guy in front of me. So I'm just doing it. I'm going 0.48 times 1900. And the answer we get is 912 people out of 1900. So can you imagine p-hat is 912 on the top out of 1900 people in the bottom, right? That's 48%. Now I'm ready for salt. Make sure it's one sample proportion. I can now put in the number 912, and the number of trials is 1900. And this fella is 0.5, and we're trying to prove that it's less than 0.5. Right, that was the null hypothesis. Was it less? And I'll generate the results. And this guy is a z-score, and this guy is the p-value. Okay, so copy this guy. There's your test statistic to 2 decimal places. And then here is your p-value. Put that in the right spot. They want 4 decimal places for that guy. So far, so good. Are we happy about the p-value, which is really the important one? Okay, we're getting thumbs up. I like thumbs up. Right, so we're kind of getting to the conclusion part, right? The end of the line.
Happy to help.
Oh, somebody said they were happy to help. It must have been electronic. Did you hear that? Weird. Yeah. Oh, okay, so focused on it. So we're going to do it based on the p-value. Is this guy here, right? Is it less than the alpha, which is 0.05? So is 0.0406 less than 0.05? Right, not agree? Right, so how do we phrase that? The p-value is less than the stated significance level of 0.05. You see, we kind of use some English and some numbers to do that. So there is sufficient evidence to conclude that the headline is justified. In other words, he is allowed to say that less than 0.5%, right? Less than 50%, less than half Americans are happy. I wish he hadn't used the word significant, right? Because I think that is a little bit disingenuous, because when people hear that word, they are thinking it's a lot less than half. And it wasn't really, wasn't it? Only a couple. And this sentence here is basically them giving me the opportunity to have my little rant that statistically less than 50% doesn't necessarily mean it's a lot less than 50%, or some sentence along those lines. Now, why can that difference between statistically significant, which this is, because we're using the word significant in a statistics context, right? And this is statistically significant. It is less than 0.5. Why is that different than practical importance? If you are not told what the data is, but you're only told the conclusion, couldn't you come up with a false impression of how important that information is? If I said to you, it is statistically significant, let's phrase it a better way, statistically significant number of people who eat carrots die of colon cancer compared to those who don't, wouldn't that scare you off eating carrots? If the reality was that 0.004% of people who eat carrots get colon cancer, and 0.0000399% who don't eat carrots get colon cancer, can you see that you could probably eat carrots with complete safety? Statistically, there was enough evidence because you had a huge sample, and if you make your sample big enough, you know you'll find a difference. No matter how small it is, you will eventually find it, right? And then you can do this statistically significant bit and scare the EBGBs out of everybody. So you want to make sure that whenever they hit you with that, oh, it's been statistically proven, blah, 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 you would be wise to say, tell me your P and your P hat, right? Tell me what your hypothesis was. Let me see the difference between them. And then I'll make up my mind if that difference is important enough for me to change my life. I could quite easily tell you, because it is true, that your chances of being killed in a car accident are significantly less if you're traveling at 30 miles an hour when you have the accident than if you're traveling at 70 miles an hour. I think everyone would say that's kind of common sense, right? And that's why we have speed limits, right? That's why some roads are 60 and some roads are 30. But if you take that to its conclusion, its silly conclusion, then shouldn't the speed limit be 3 miles an hour everywhere? Because if you have an accident at 3 miles per hour, won't you be statistically less likely to be harmed than at 30 miles an hour? In your life, don't you have to make risk analysis choices? I do things that will kill me, potentially. But my life would be a pain in the butt if I couldn't drive. Let's be silly. Don't stairs kill people because they fall down them? Should we now abolish all stairs? Every building in the universe should now be ranch style. Flying kills you, or potentially do. Should we ban aircraft? Olivia, why you want to ban aircraft? Stop doing that. But can you see the problem with life is you will take risks. Everything you do will kill you, potentially. Some of those things have such a small chance of killing you, I am willing to risk my life to have a life in the first place. Now, other things will kill me a lot quicker. That's why I suggest very strongly that you don't take illegal drugs. The benefit, whatever that is, which I can't see any, is not worth the chances that you'll probably die prematurely. So you have that risk analysis in your life. And I've ranted on
Give
it.
all of us extra credit.
That worked really well up until the last part of the sentence. And in fact, I might keep that part in so everybody can know what you're like, Jade. Oh, she keeps on asking for extra credit, does she? Okay, no, I won't do that. Okay, but at least I now know why that last two questions didn't work, so I'm happy. So we're on to our next section. And chapter 11C, like everything that's going to happen to the end of this course, is a
12C?
hypothesis test. Thank you.
12C?
12C it is. Hypothesis test for the difference between two population portions. Well, I mean, it kind of makes sense that that would be the next one, right? We've looked at hypothesis testing when it was a single proportion, and now we're going to look at hypothesis testing when we want to compare two different proportions. So let's give you a story. Population 1 is going to be Scottish people. And we collected a sample of 250 of them. And we found out that 120 of them out of 250 had been to France. So you did a survey in Scottish adults, you found 250 random sample, you asked how many of them have been to France, and 120 said they had. If you live in Scotland, because I've done it, you can actually fly to Paris in about 2 hours. It ain't far away. And then population 2. We'll have them as the Americans. And we have to ask them the same question. But this time, for no particular reason, the sample is 300. And when we ask them, out of that 300, 120 had been to France. So what we would like to do in any hypothesis test when we have two populations is, we'd like to find out, is there evidence to prove that they are different in some way? And to do that, we set up a null and an alternate, and there are 3 of them, 3 different versions. The null hypothesis is always going to be that the two populations have the same proportion, right? They're both equal. But we don't write it that way, typically. We write it this way. Are you happy that mathematically this and this is the same thing? If P1 is equal to P2, won't P1 take away P2 be equal to 0? Isn't that just another way of saying it? Now, what is the alternates? Well, couldn't P1 be bigger than P2? Isn't that one of the possible things? Couldn't the first population have a bigger answer than the second? We don't write it that way. We write it typically that way. So this is the normal way to write the null hypothesis, and this is the usual way of writing the alternate. And this would be for Scots guys bigger than American guys, right? Now, if we did the second possibility, said there's 3, the null hypothesis doesn't change. So that makes your life dead easy. the null hypothesis will always be typically the ones we're going to do, that they're equal to each other. And the alternate hypothesis, well, isn't this one, the first guy is bigger than the second? What would that represent? If this means the first population has a bigger answer than the second population, what would this mean?
The opposite.
Which is the first one population has an answer that's less than the other one. Now, you can pretty much figure out that isn't the last one of the three going to be that they're just different, right? They're not the same as each other. This guy here, is he a right-tailed, a left-tailed, or a two-tailed test? What name do you give to this fella? Right-tailed, left-tailed, or two-tailed? What do you think?
I'm gonna guess. Is it right?
Correct.
Okay.
What was your, I mean, it could have just been a pure guess, but was there something that kind of made you go right rather than any of the other choices?
If it's greater than, I just assumed that it would go to the right.
And you are correct, and that's how you tell. Greater than, you go to the right, right-tailed. Pretty obvious then that won't this one be left-tailed? And two-tailed. In case you get some questions that ask you about what kind of test is this, is it a left or right? Or, I think they only call it a one-tailed or a two-tailed, isn't that the choices that you get in this homework? One-tailed or two-tailed, but I think it's better to know the two flavors of one-tailed. So we have got all this basic stuff, but doesn't it still boil down to you just have a null and alternate, right? Now, in this particular story, just looking at the data, doesn't it look pretty obvious that Scots are, more of them have been to France than Americans? Would you, just looking at the raw data, does that seem reasonable? Great. So for this story, the null hypothesis is going to be that guy, and the alternate, damn it in space, it's going to be that guy. That's cool. And can we have a significance level of, say, 1%? We need that in the story. Then what's left? Well, we're going to find a p-value using SALT. And hopefully there's no binomial distributions in that. But only you lot will know what I mean when I say, I hope there's no binomial distributions in that. And everybody else is going to say, what's he talking about? He never mentioned that before. Anyway, we're going to find p-value, and then we're going to test it. Is our p-value less than that? And if the answer is yes, then yep, we've proved that Scots people do go to France more often than Americans. And if the answer is no, then we haven't proved anything. There's only one last thing to talk about, and then we'll actually start doing these questions. And that is the conditions. And you say, what do you mean the conditions? Well, two major ones that at least they're concerned about. Shouldn't all the samples be random? Right? The population, you know, the sample that I got a Scots guy should be a nice random sample, and so should the American ones. And remember a guy called N P naught and N 1 minus P naught? Remember those two guys? Don't they have to both be bigger than 10? Well, when there's two samples, there isn't a P naught. What there is instead is the NP1 has to be bigger than 10, and N1 P 1 minus P1 has to be bigger than 10. And N2, P2 has to be bigger than 10. And N2, 1 minus P2 has to be bigger than 10. Basically, don't you just do lots of the 10 rule, right? Let's look at my sample. I don't have a P1 or a P2. Don't I have a P1 hat and a P2 hat? Great. So we just adapt it. 120 said yes, 130 said no. Both of them are bigger than 10. 120 said yes, 180 said no. Both of them are bigger than 10. Do you see that I could check these very quickly? Now we're ready. Do you think that there's a big enough difference between the Scots and the American data that we will get a statistically significant result and be able to prove that actually more Scottish people go to France than Americans? What's your gut feeling? Do you think they're different enough or not?
I think maybe.
So maybe that's a cover in it. A maybe. Come on. Yes or no? What are you going for?
Yes, because I feel like the population, it's still kind of small. Like 250 and 300, like I feel like 50 people is gonna make enough of a difference, especially if it's only to the 0.01. I think we might be on to something.
Okay, let's find out. I have no idea, by the way. My gut feeling, if I had to guess, is it's probably going to work. Right, that's just my gut feeling. I've been proved many times wrong, which is why you need hypothesis testing, because it gives me numbers that tell me whether that's the correct thing or not. So I'm just going to use this salt button, and then I'll go to the second one. So click on this one, inferential statistics, and do you see that there's a different choice? Do you see the two sample proportion? But it's pretty much what you'd expect it to be, right? The first one is Scottish, guys. So that was what, 120? Whoops, better rub that out. 120 out of 250. And the second one was the Americans, which was also 120, but that was out of 300. Why do I keep doing that? 120 out of 300. And the difference is 0. Now, what does that 0 mean? That's P1 take away P2 equals 0, which are the only ones we're going to deal with. You can actually adjust it and have the difference between them is 0.1 and then test, is it more than 0.1, right? But that's a little bit more of a nuance that we aren't going into. We're just going to leave that guy as 0. And in this particular story, aren't we interested in proving that the first guy is bigger, right? So it's greater than. Now, when I hit generate results, I come up with a p-value of 0.029, which I'm just going to round off. What shall I round off to? To 0.03, right? So that's a 2 decimal place. Okay, let's return and see what our conclusion looks like then. Based on the data that we collected here, this is our p-value. Is this p-value less than our significance level of alpha? Well, is 0.03 less than the 0.01? Remember, I picked a 0.01 in this story. We, both of us, Jade, you and me, we are both wrong. This is not statistically significant, right? There's not enough evidence to prove that Scottish people have gone to France more often than Americans.
So would
Now,
there need to be more Scottish people that have visited France for it to have worked?
yeah, pretty much. If this had been 140, we probably would have had evidence. Actually, if this had been 130, we probably would have had evidence. Right? We just needed a few more Scottish people out the total, and it would have worked. On the other hand, if I had said, "Oh, let's use the standard one," wouldn't the answer be yes now? If I said use this significance level, wouldn't the p-value be less than 0.05? And wouldn't we have said, hey, we've proved that Scots people do in fact? Now, you might think, well, how can we say yes and then we can say no? I mean, that sounds like we're cheating. Well, in a lot of ways, if I did what I just said, I would be cheating, wouldn't I? I decided right at the start, I was going to live or die by that alpha. So if the answer is no, I got to live by it. I've got to say I didn't find evidence. What I can't do, or should never do, is find the p-value and then pick the alpha. Can you see how that's peeking at the data? Is the usual phrase for that, right? You're finding the p-value before you choose the alpha. Not an acceptable way to do any kind of true science, right? Now, if you want to make sure that you're more likely to win than not, shouldn't you pick a significance level of 0.1? You know, alpha equals 0.1, because won't that get you the most number of times a significant result? But if you do a 0.1, does it not mean you're also going to be wrong 10% of the time? In other words, you're going to say, I proved this, and 10% of the things that you said I have proved, you didn't prove them. The truth was actually the exact opposite of what you said. I don't want to be in an aircraft that was built using an alpha of 10%, where, yeah, that part works fine and that part works fine, if 1 in 10 of them doesn't. Because it might be something important like a wheel or a door. And that would not be if you're building spacecraft, don't you want that alpha to be really small? What's the chance that this will fail in flight?
Yeah, you could have an O-ring made 2 years ago.
Yeah, a simple thing like that. I think they didn't test.
Yeah,
I think it got really cold before it got
got
really
too
hot.
cold for them, and the engineers warned them that it was too cold, but nobody paid attention.
Sounds about right when it comes to governments. Okay, guys, so far so good. Do you like the idea that the difference in two proportions is not that different from how we did one? I mean, it's going to be very similar. So what I'm doing right now, you can bear with me for a few moments, is I'm closing a whole load of windows, and we're going to go in and look at some of the homework questions from that section, which is 12C, which is what I'm opening right now. And there are excuse me, I'm still looking for a question I like. Here we go. I found one. Oh, I'm having, what's that called? Technical difficulties. Here we go. Right. I'll make this bigger for my eyesight, even if it's not for yours. Right. So this is going to be question 5. So what I want you to do. That 4? Yeah, 5. Oh, it's too much. Shrink it back out. It's weird it does that. I just noticed that this thing is not complete. I have more questions to add, so obviously I got distracted when I was making it. Anyway, a survey. Oh, darn it in space. Yeah, it does that. I don't want the key, go away. Here we go, right. A survey was conducted which asked college students whether they would return money if they found it in a wallet. They've done this story in lots of ways. I recognize it. And in this particular one, they're doing it as two populations, right? Women and men, or self-identified women or men. Of the 93 women, 89 said they would. So I'm going to call population one women. And population two is men. Now, what do I know about the women? Well, the sample, it was 89 out of 93. That's P1 hat. Now, the men was 57 out of 75 who said they would return the money. We're making assumptions that these represent college students. Test the null hypothesis that equal proportions of men and women would say they would return the money versus the alternate that the women are higher. Okay, so let me just go out a bit and kind of put that on paper. So what we got here is the null hypothesis is that they're equal. And the alternate hypothesis is that women are more honest, right? They return it more often than men. So the difference more, greater than. Are you happy about the null and alternate? Are we good? Always equal 0 in this case. Prove that's bigger than that. Right. So time to use salt. Right, when I click on this fella, inferential, two sample proportion, the women go first, 89 out of 93. The men go second, 57 out of 75. That's always 0. We're trying to see that women bigger than men. And we're going to generate the results. Boom. And that's your Z statistic. And that is a very tiny p-value. What guy am I looking at?
That's 12B.
Okay, I'm now looking at the right one. Can you see the window? Question
Yeah.
5? Okay,
Yeah.
so the p-value that we want goes in here. Right. And the test statistic was that Z score, which I now can't remember what it was, but whatever the Z score was, you put it here. This guy here, you're going to put, that's interesting. How am I going to do this? I need to check something out.
I think it says use woman, take away men.
Oh, so I can't use the p-values? Oh, well, try the p-values first. Can someone on theirs do that? Because I don't have it on student view now, so I can't check my answers. Can you type in P1 minus P2 equals 0? Will it accept that?
No.
No. Okay, so let's try women take away men.
I believe there's a subscript button as well.
Oh, that's our third possibility. Try women take away men. Tell me if that works.
Oh, like women minus men?
Yeah.
Okay.
Nathan, if you've got the chance, do you want to try the subscript one? All we're trying to do is figure out how to make the software understand what we're saying.
That doesn't work either.
Is it not taking women, take away men?
Nope.
Okay, so we must be looking for the subscripts. Let's
Yeah,
do it
if you-
then.
the subscripts, I believe, under functions.
Okay, strange place to put it, but here, P, functions, subscript,
That's that top one, yeah.
and then put in 1, move to the right, subtract, P, subscript, 2, move to the right. Okay, try that one.
I'm working on that one. Hold on.
Okay. Uh,
Yeah, that one worked.
that's right. Here's a little trick. Copy, paste, and then you only need to change one symbol. Okay, so we got our p-value. To 4 decimal places. 1, 2, 3, 4. Oh, well, that would have to round up to a 1 then. Since the p-value is less than the significance level, we reject H naught. This means that there is sufficient evidence to conclude that women would return the more money more often than men. So that's just how we do the conclusion part, right? Since this number is less than 0.5, so the p-value is less than the significance level, we reject H naught. And this means sufficient evidence then to conclude. Well, we've learned something that you need to use subscripts and it won't allow any other choices. I can see me getting lots of emails in the next few days where people have done the P1 that I did and said, I typed it in, but it ain't working. So a quick P1 use subscripts, right? Remember that, guys. P1 uses subscripts.
I have a question. So
Yes.
for this, you went to inferential statistics and then it's under the 2 sample proportion, right?
Yes.
Okay.
Okay. Let's do a last one. Yeah, I've got some business I have to deal with. We're going to continue with this tomorrow anyway, right? There's going to be a little overlap. So it's not like this is the end of these questions. What do I want to do? Do I want to do ear piercings? Nah, don't like that one. It sounds boring. That sounds general. We did date. Okay, let's do dating ones. In a certain survey, college students were asked the question, would you date someone with a great personality, even although they did not find them attractive? I would, but it's back in the day. Of the 100 women, 63% of them said yes, they would. And of the 80 men, 42.5% said yes. So there's the data for P1 is 63%, right? And the data for P2 hat is 42.5%. But in order to use SALT, don't I need the X and the N? And it's not going to be too difficult for the first one, the women. Would you agree that 63% of 100 ends up being 63 women? Right? So I'm writing that number down, that P1 hat is 63 over 100. I'll need that in a little while. Now, the men are 42.5% of 80. So I'm not going to do that in my head, but I am going to do it as a calculation. at 42.5, right? And I get, it was 34 men. So 34 men out of 80, okay? Significance level, thankfully they have told us it's 0.05 that I like. And one is women, yep, we got that, and 2 is men, we got that. So everything that we need is going to be here. So we'll start off with the null hypothesis. P, hit the function button, top left-hand corner, 1. There's P1. Then move it along, take away P subscript 2, move it along with your arrow, equals 0. And what we want to prove, is there sufficient evidence to conclude that the population retribution a higher proportion of women? Okay, so it's this guy, bigger than 0, right? That's the alternative. Now I can use salt, and I should be able to do it. Inferential, gotcha. 2 sample proportion. The number of women was 63 out of 100. And 57 out of 75. That's all with 0, and we're trying to prove that women are bigger proportion would do that than men, so it's a greater than. Generate the results. Did I do that right?
You have to input the men in there.
Oh, did I get the men and women back to front?
You did the women, but you didn't change the men.
Oh, the men was 34 out.
80 and 42.5.
Right, so it's 34 men out of 80. Right, that's what I should have used, right? 34 out of 80. Right, let's do it now. Well, that's much more reasonable. Here's the p-value. Okay, I've lost my question. Let me go hunting for it. Here it is. There's my p-value, 4 decimal places. I think that guy rounds up to a 1 then. Is our p-value less than 0.5? So let's see. Since our p-value is less than the significance level, we would reject H0. This means that there is sufficient evidence. Okay. So what we've proved here is that women would be more likely to date someone that had a great personality, even if they didn't find them attractive, than men. So that just proves how superficial men are, right? Compared to someone. Are we good? Any questions about that?
I have a question. Could you just go back to salt for 1 second, just so I can
Sure.
see why mine doesn't come up to the same stuff as yours?
Okay, so I'll have to do it again, but that's fine. 2 proportion.
Hmm,
The women goes first, and the women were 63 out of 100.
Yeah.
And the men
34.
out of 80.
Mhm.
And then we're trying to prove that the women larger percentage, so it's a greater than
Okay.
effect. Then I generate results, and there is my p-value.
Perfect. Got it.
Got it?
Mhm.
Any other questions right now?